Hello everyone, I am Claire Prudhomme from the Ice Remains Institute in Germany, and I am going to present you the work resulting from my doctoral thesis carried out at the University of Bourgogne-Franche-Comté. My work consisted in the development of a decision support approach to evaluate the implementation of disaster management plans. Assessing the applicability and effectiveness of a plan requires consideration of several factors. Let's take the example of plans in various disaster situations such as flood, the COVID-19 pandemic, fire, and earthquake. In each of these situations, the plans are first of all composed of different actors such as police, firefighter, ambulances, hospital staff, and in the case of the COVID pandemic, the population itself. Then, a plan can address various levels of disaster such as municipal, regional, national, European or international. Containment of a city or a country is a different kind of resource management. The specific context in which the plan is applied, the locality and the reason for its application affect the applicability of the plan and its effectiveness. The objective of a plan, for example, whether it is intended to be curative or preventive, or the time of year in which the plan is applied, are all factors of impact. Indeed, there may be variation if it is applied in the middle of summer or winter, for example. Providing a decision support tools that consider all of these factors requires studying the impact of each of them on the plan, but also the impact of the combination of these factors on each other, which can lead to complicated situations. The best way to study these factors and their interplay is to apply them. Also, some plans are studied directly by application. It is often better to simulate their application. Simulating the application of plans through practical exercise is often very costly, but thanks to the evolution of artificial intelligence, it becomes interesting to simulate the application of plans in a virtual way. However, simulating the application of several different plans with multiple different factors requires generating as many simulations as there are combinations of these factors and plans. While some factors such as the amount of resources or the amount of population can be seen as a simulation parameter that is incremented or decremented, other factors cannot be considered as parameter but require the integration of complex physical models or even changing the type of simulation completely. When the change of factor is big enough to imply to change the foundation of the simulation and thus to change the code of the simulation and to redo this simulation, that can become very complex and expensive. For example, the simulation of the application of the containment plan of the city of Dijon is different from the simulation of the application of the plan to fight a fire. This requires the implementation of different simulations. So, the problem addressed by the thesis was how to manage the diversity of simulation implementation required for decision making. To solve this problem of simulation implementation, the thesis work consisted in the elaboration of a framework allowing to generate multi-agent simulation from a knowledge base. Multi-agent simulation are the most suitable simulation for disaster management and for simulating the application of plans. The automatic generation of this simulation is based on the use of human knowledge that is explicitly described in an ontology. This knowledge is of various types. The first type includes knowledge that can be described as disaster management business knowledge, corresponding to knowledge related to the plan, such as actors, hospital staff, police, for example, geospatial knowledge, demographic knowledge, and resource management. The second type of knowledge is the knowledge related to the multi-agent simulation modeling, such as how the agents are designed, the representation of the resources, the environment, the interaction between the agent and the resources, and the interaction between the agent and the environment. Finally, the last type of knowledge is the one allowing the automatic implementation of these simulations. This is the technical knowledge of programming the simulation. This knowledge is used to dynamically implement the model. The thesis work consisted in linking these three types of knowledge to automatically generate the simulation adapted to the different contexts we wish to simulate. These three types of knowledge are structured in such a way that they can be related. The primary basics of disaster management and plan application are defined in an ontology called SEMDM. The primary basics of simulation management, such as the multi-agent model and the interaction between agents, environment, and resources, are defined in an ontology called SEMMAS. This ontology, SEMMAS, also contains the technical knowledge related to the simulation implementation. Simulation generation starts with the integration of business knowledge in the SEMDM ontology according to the application case. If we take, for example, the application of the containment plan of the city of Dijon, this consists in describing the containment plan, the spatial knowledge of the city of Dijon, and the demography of Dijon. In this case, it corresponds to retrieve and interpret the geospatial files, GeoJSON or shapefile, for example, of the city of Dijon, to define the number of actors and their roles, such as the policemen, aiming at the verification of the respect of the containment, the hospital staff taking care of the people affected by the virus, and the inhabitants subjected to the rules of containment and likely to be infected. Then, a set of logical rules is used to enrich the knowledge in SEMMAS about the agents, the environment, and the resources. Following the integration of the knowledge about a plan, the different agents are defined with a set of behavior associated to each of them. This behavior can be complex, such as caring for or transporting a person from the disaster site to an advanced medical post, or simple, such as moving. Thus, the information about the environment, the resources, and the agents are defined in the multi-agent paradigm. In our example, it will correspond to use the demographic knowledge to define the number of agents and the knowledge on their role, such as population, firemen, policemen, hospital staff, to define the different types of agents, and the knowledge on their action to define the different behavior associated to each type of agent. It then remains to automatically implement the simulation model. The implementation of the simulation model depends on the multi-agent simulation platform used for the execution of the model. The platform, which has been chosen, is the Gamma platform for its ability to manage geospatial data and its capacity to extend complex agent behaviors. This platform allows to describe the different behaviors of an agent through attributes and skill functions, and also to combine them. These behaviors are defined according to the triggers, on which criterion this behavior must be applied. They are then stored as a library of possible behavior for the agent. This library is the dynamic portion of code that needs to be enriched to add new agent behaviors. This extended behavior library is used to dynamically generate code based on the knowledge described about the agent in SEMMAS. Thanks to the combination of the knowledge on the multi-agent simulation and the dynamic library of multi-agent behavior implemented in the Gamma platform, an automatic process allows to generate the source code of the simulation and to execute it in order to study the plan and to provide a useful evaluation for the decision-making on its application. For example, here is the theoretical result of the simulation corresponding to the application of the population containment plan in the city of Dijon. The COVID-19 disease spreading of this simulation has been initialized through an infected agent. This video shows the result of containment rules application, such as closing schools, activating the barrier gesture, stopping leisure activities, and a full lockdown after a certain time of pandemic spreading. In this video, agents are represented through circles with different colors according to their health state. Another example is the application of the NOVI Plan to the city of Montbard following the simulation of a fire at the Paul-Éluard multipurpose hall. In this NOVI Plan, firemen in green rescue the victims from the disaster site to the advanced medical post. The physicians in dark blue are distributed between the advanced medical post for first care and the hospital for full caring. The ambulances in light blue transport the victims from the advanced medical post to the hospital. After the application of this simulation and the variation of the different parameters, the different results are collected and studied in order to provide a decision support. For example, the collection of information on the execution of the NOVI Plan in Montbard highlights in which situation the plan is effective and in which situation it is not. It also allows a better distribution of physicians between the advanced medical post and the hospital according to the estimated number of victims. To conclude, this type of decision support can be a real advantage for smart cities to verify and evaluate the effectiveness of disaster management action plans that are defined for the city dynamically according to infrastructure changes. Thank you for your attention. If you have any question, do not hesitate to contact me by email